All right, let's just jump right in. Get this, you've got two molecules that are practically twins, almost identical, but when you put them in a reaction, one of them zooms off like a sprinter, and the other is 1,000 times slower. How is that even possible? How can one tiny little change have such a massive, massive effect on speed? Well, that's the exact mystery we're going to solve today.
So that's what we're going to dig into. We're cracking the chemical code. It's all about learning to look at a molecule's structure and see it not just as a collection of atoms, but as a blueprint that tells us exactly how it's going to behave.
And here's our game plan. First up, we've got to learn the language chemists use to tell these stories. Then, we'll walk through a classic chemical reaction, but stick with me, because there's a huge plot twist coming. After that, we'll uncover the secret code that explains everything. And finally, we'll see how that code lets us predict the chemical future.
Okay, first things first. Before you can understand any story, you need to know the language, right? For chemists, that language is all about showing how and why reactions happen.
You know, at the very heart of it all, every single chemical reaction is just about electrons moving around. That's it. Think of it like a simple circuit. You've got a source, where the electrons come from, and a sink, where they're heading. This simple flow is what makes and breaks bonds. It's what creates, well, everything.
So, how do we actually draw this? Chemists have this awesome shorthand called arrow pushing, and it's got 3 dead simple rules. Rule number 1, the arrows show where pairs of electrons are going. Rule number 2, and this is super important, arrows never show atoms themselves moving. It's all about the electrons. And finally, rule number 3, the arrow always starts at the electron source and points right to the electron sink. You get these 3 rules down, you're basically fluent in chemist. All right, now that we know the language, let's read our first story, electrophilic aromatic substitution. And hey, don't let the name intimidate you. It's actually a pretty simple tale about a molecule that just wants to keep its cool.
So these things called aromatic rings, like benzene, are incredibly stable. Seriously, they are the VIPs of the molecule world. I like to think of them as this super exclusive members-only club. They have this special arrangement of electrons that makes them really, really happy. And they will fight like crazy to maintain that stability. They do not just let anyone in.
So here's where the drama starts. Even though it's a stable club, if a really, really attractive newcomer shows up, something we call a strong electrophile, the ring just can't help itself. It reaches out and attacks. But this move comes at a huge cost. To do this, the ring has to temporarily give up its special VIP status, breaking its perfect, stable system. It becomes this awkward, unstable thing. This is the hardest, most difficult part of the whole story.
But this awkward phase, it doesn't last. The molecule is desperate to get its exclusive status back, so it does something really clever. It kicks out one of its old, boring members, just a simple proton, and poof, just like that, the stable, happy, aromatic club is back in business, but now with the new member where the old one used to be. Okay, but this is where the story gets really interesting. That was the simple version. What happens if our exclusive club already has a special member attached to it before the story even begins? Well, it turns out that one single member, a substituent, can change the entire narrative. And when I say change the narrative, I mean it can flip the whole script. Imagine adding one tiny little group to our molecule, and the reaction doesn't just slow down, it grinds to a near total halt. We're talking 100,000 times slower. That's not a small difference. That's a chemical shutdown.
Just look at this. On the left, we've got a methoxy group. That reaction becomes 10,000 times faster. It's like putting a rocket booster on it. On the right, we swap that out for a nitro group, and the reaction slams on the brakes, becoming 100,000 times slower. It's the exact same core reaction. The only thing that's different is the guest that was already in the club. So, what is the deal here?
Well, after seeing this happen over and over again, chemists started to notice a pattern. These substituents, these special members, they aren't random. They fall into these predictable groups. Some are activating. They speed the reaction up and tell the newcomer where to sit. Others are deactivating. They slow things down and point to a totally different seat. And then there's this third, kind of weird group that slows things down but points to the same seats as the activators. A pattern was definitely there, but what was the secret rule behind it all?
So, how do we go from just seeing these patterns to actually predicting them? This is where we go from being chemical detectives to being chemical fortune tellers. We need to crack the code. And the key was a brilliant equation from a guy named Lewis Hammett. This right here, this is the Hammett equation. Now, it might look a little intense, but the idea behind it is actually beautiful. It's what's called a linear free energy relationship. And what it basically says is that there's a simple, predictable connection between a molecule's structure and how fast it reacts. This was huge. It was the first real mathematical bridge between kinetics, how fast things go, and the underlying stability of the molecules themselves.
The equation has two really important parts. First up is sigma. You can think of sigma as the substituent's personality profile. It's just a number that tells us if the group is generous with its electrons, an electron donator, or if it's greedy and pulls electrons away, an electron withdrawer. Then you have rho. Rho tells us how much the reaction itself even cares about that substituent's personality. Is it super sensitive, or does it not really matter?
Let's make this real. An amino group has a big negative sigma value. That means it's a strong electron donator. Now, what about our nitro group from before, the one that slammed on the brakes? Look at that. It has a large positive sigma value, making it a powerful electron withdrawer. We can now put a number on it. We can quantify the exact electronic personality of any group. Okay, this is the grand finale. We've learned the language, we've seen the wild plot twist, and now we have found the secret code. So let's put it all together and see how this amazing tool lets chemists see the future. This rho value, it's like a crystal ball. Just by looking at its sign, positive or negative, chemists can figure out what's happening in that hardest, most critical step of the reaction. If rho is negative, like in our exclusive club story, that tells us positive charge is building up. And so it makes perfect sense that any electron donating group, one with a negative sigma, is going to speed things right up. It all clicks into place. The code works. You know, it's easy for us to look back and think this is all obvious. But at the time, this was a radical idea. As Hammett himself said, this whole concept of linking reaction speed to stability was something people argued about constantly. But he proved it. He did the hard work of measuring and showed everyone that the connection was real. And in the process, he totally changed the game. And that brings us full circle. We started with this crazy mystery about reaction speeds, and we found a code that doesn't just explain what happened, it lets us predict what will happen. And this power of prediction, that's why all this matters. This isn't just a fun academic exercise. It's how scientists can design life-saving drugs, create incredible new materials, and solve some of the world's biggest problems. Which really leaves us with the big question. Now that we can predict how molecules will act, what amazing problems are we going to solve next?